as requested, I will be going over a problem related to galvanic cells and finding the standard electromotive force, otherwise known as the cell potential. So let's take a closer look at this question because you will be encountering these types of problems in the review. Let's get started. So the problem states, a galvanic cell consists of a magnesium electrode in a 1M magnesium nitrate solution and a silver electrode in a 1M silver nitrate solution. We are to calculate the standard electromotive force, that is, the voltage or electric potential of this galvanic cell. Well, first things first, I would like you to refer to the standard reduction potentials chart that was provided to you a couple of sessions ago. In there, you can find the electric potential provided by the reduction of silver and magnesium. So if we take a closer look at that, we will find that for silver, when it gains one electron, about 0.8 volts are provided. Looking now at magnesium, we see that when magnesium gains 2 electrons, negative 2.37 volts are produced. We will be using these voltages to find the total cell potential of this galvanic cell, the total electric potential of the cell. But before we do so, we must first figure out what the anode and the cathode of our battery or our galvanic cell is. In order to do so, let's refer back to the chart that shows the electronegativity of each of these elements. If you look closely at that chart, you will find that magnesium has a smaller electronegativity than silver. This means that silver is the oxidizing agent of magnesium. In other words, silver will oxidize magnesium. That means that magnesium will be the element losing the electrons, therefore making it our oxidation half reaction. So let's take a look at our half reactions next. As stated, our oxidation will be from the side of magnesium, simply because silver has a larger electronegativity than magnesium. Therefore, magnesium will be forced to release its electrons in order for silver to take them. That makes magnesium our anode. Okay, so the half reaction for magnesium will become our anode since it's losing the electrons. That leaves our reduction to be from the silver. The silver will be gaining electrons, making this our cathode. I hope you can see that. Excellent. Next, before we continue, we must first make sure that the number of electrons are balanced. As you can see, the original oxidation half reaction shows that magnesium will release 2 electrons. However, silver will only be gaining 1. In order for us to balance the number of electrons, we must first multiply the reduction reaction, or the reduction half reaction, of silver by 2. This will allow the electrons to become balanced, and in the process, every other element or ion will also be multiplied by 2, as you can see. Finally, it is time to combine both half reactions. As you can see right here in the bottom, on the reactants side, we have solid magnesium plus 2 silver cations, okay? And this will yield 1 magnesium 2+ cation and 2 silver neutral atoms. Now remember that this is also aqueous. I forgot to write that there because it is in its ionic form. Excellent. Now that we have our final redox reaction, let's put this in terms of our cell diagram. So we have a half reaction for oxidation of magnesium and a half reaction for reduction of silver. Let's see what the cell diagram for that looks like. So if you remember the structure of the cell diagram, it will consist of your cathode and your anode. In this case, we have written our anode first as the oxidation of solid magnesium into a magnesium cation. The 2 double lines represent the salt bridge or the electrolyte. On the right hand side, we can see the 2 silver cations that are going to gain electrons from magnesium to become 2 silver stable atoms. These are in the solid form. Excellent. With our cell diagram, we can now refer back to the electric potential equation to find the electric potential of our cell. If you recall, electric potential of our galvanic cell could be found by simply subtracting the electric potential of the anode from the electric potential of the cathode. The values that we found in the very beginning for the reductions of silver and magnesium were 0.8 for the silver and negative 2.37 for the magnesium. Let me repeat that just in case I said it incorrectly. For the silver, it is 0.8 volts. For the magnesium reduction, it was negative 2.37 volts. But before I plug those values in, I want to now replace the cathode and the anode with a proper reaction here. So I'm going to now show the electric potential for each reduction. The electric potential of a silver reduction is shown as electric potential of silver slash and then the neutral atom. The same is shown for the anode. The electric potential of magnesium ion into the neutral atom. Remember, the values were 0.8 and negative 2.37 respectively. You can always rewind to see those in the beginning of the video. Here, I've substituted these values or these symbols with their corresponding voltage. Remember that the voltage for the magnesium reduction was negative 2.37, so that's what we're plugging in there. That will make it so that when you subtract a negative number, you will be essentially adding 2 positive numbers. The final value of the electric potential comes out to a positive 3.17 volts. Therefore, our galvanic cell is able to produce 3.17 volts. The positive value of this voltage or of this electric potential shows us that our reaction is favored in the forward direction. Had we seen a negative value instead for the final electric potential, that means that the reaction would have been favored in the reverse direction. I hope this helps you understand how to approach these cell diagrams or galvanic cell problems. Thank you, and I hope you enjoyed this tutorial.